Got it. Do we need to start? Are we good? Everybody good? Perfect. So that's extremely important because it's gonna create the perspective on what type of design and construction you're gonna get into, what type of materials you're gonna get into. So when we talk about service life and durability, all of these different cases are gonna have completely different challenges. So one thing I like to always show when I talk about this at the introduction is the perspective of concrete and where the concrete goes and what type of operations you're going to get into or what type of design. So this is a project that actually we did in the Colorado Springs area, and we were in charge of the bridge. That's a pedestrian bridge. It's an architectural feature to the whole entire project. But you can see all the question marks I have, and all I want you to think about is, what are all those different areas that you're going to have, where the concrete is going to go, what type of design you're going to have, what type of specs you're going to have, what type of concrete materials you're going to use, right? And even what type of durability and service life considerations you need to have for all of them. They're not going to be the same, right? And if you see where I'm going is that concrete, it doesn't matter, it looks the same. It's never going to be the same. You're going to have completely different demands for construction, completely different demands for design, and you're also going to have completely different exposure conditions that are going to drive the performance of the material in service. So for us to understand, obviously, how concrete works and how we can make concrete durable, we need to understand all of this. Otherwise, we cannot make good solutions for the concrete. So what are the things that you're hearing from me, and where do you believe the standards need to go? Well, from a durability and service perspective, we need a standard that has, all things durability. Try to cover all the areas of durability, right? Try to make sure that we have standards for planning, designing, construction, and maintaining those structures that you're going to build, right? Multidiscipline and knowledge base. Consensus need to be multidiscipline and knowledge base. Realistic and constructible. We cannot just start thinking and dreaming that we're going to be able to do things that are just right in the lab, but not in the field. We need to be realistic, including alternatives, prescriptive alternatives, because sometimes you need to move fast and you need to get the job done. Sometimes you can spend a little more time and do performance testing and qualification, right? Then you also need to make sure there's going to be different applications and different type of projects you're going to be using all that concrete, right? And then the last one that I mentioned is recognizing the difference, or how durability differs from service life. Extremely important. Durability is not the same as service life. So all of those things are some of the things that we have in the wish list, and we have been working in the wish list over many years. Now, the good thing is that we are now working on it in ACI. There was a committee established to work on the first durability code. It will be the first of its kind. It's not going to be specific to a structure. It's going to be a first durability code for the industry where you can actually find the right requirements and be able to fit the requirements to your different applications. We're working on that, and hopefully we have that ready in the next 5 to 6 years. So then let's talk about durability and service life. And why durability and service life is important? Well, the science of progress. And I would say this presentation is an important thing, right? We're talking about it. And talking about durability and service life is extremely important, okay? It's not just one more thing that shows up in a code or a project. It's actually, we are talking. We want to see how actually we can improve it. The center, right? The Center for Durability and Life Extension that we have with the university, extremely important. We're actually putting research, academics, knowledge-based solutions behind it. Focus on sustainability within the industry, extremely important. There's obviously extreme need for reduction of carbon emissions and all that, but also the theme is actually how can we make all that sustainable? Very important too. Advancements in technology. How can we make now, for example, think about how we're going to use the supplementary cementitious materials of today that we haven't put in the system yet in the industry, but we need to start doing that because we're depleting a lot of the materials, we're changing the cement. We need to start thinking about all that, how it's going to be impact our materials and performance in concrete. Industry standards, like I mentioned, we're working on codes, we're working on actually establishing requirements that are going to feed the need of our industry. So all of that is actually signs of progress. Now, areas of improvements. Where do we see the areas of improvement? Understanding the concepts, understanding truly what durability is, what service life is, and how you can truly understand design, construction, the different type of projects, like I mentioned, the perspective of concrete, where it goes in the field, extremely important to have the right solutions. Managing and defining expectations. Not everybody's going to have the same expectations. If we put a list here, what are your expectations of one thing today? All of us are going to have different expectations, and try to get that consensus and understanding for each of us that actually understand concrete to a good extent. It's going to be different, right? So try to get realistic expectations. Enhancing models will fill data. Right now, a lot of the things we do is actually what we know today. Well, how is that going to change over the next 100 years if we want to have a 100-year service life, right? All of that needs to matter, right? Reaching consensus through standards. Go back to the standards. We need to get to those standards. A building code that doesn't recognize durability and service life is likely going to be problematic in the future. We know that, right? Sustainability goes the same. We need to start recognizing that in the same standards. So then some of the trends and challenges that we're seeing that also are going to impact, durability and service life structures. We're seeing more than 100 years. Everybody talks about 100 years. And if you know the different standards that exist, none of them in the United States or North America, and most of them in the world, have requirements for service life. All the projects do. You talk to a client and what do they say? I want that structure to be 50 years, right? I want that structure to be 75 years. I want to have 100, 125 years. You go to the standards, none of them recognize that, right? That's a big gap. That's a challenge for the industry, okay? Now the economics limitations, because the way we procure projects is not on the best value, it's not on the best technical concept. What is it? It's give me the best you can, because I have the little amount of money that I can put in that project. So all of a sudden there's a discrepancy in what do you want, what do you need, and what you can afford, right? And all of a sudden at the end, you have expectations on, I want the longest life, I want the best quality. Well, we'll do all that, but are the funds there, right? Are the clients willing to spend that extra money to get that value? Or the system doesn't allow it, right? So some of the challenges we currently have. Design code deficiencies, as I mentioned a couple of times already. Exposure conditions and maintenance in service. Many of the same codes don't even have requirements for maintenance. That's a big issue right now. And many of you know that living in Hawaii or being in coastal areas. What are the requirements for maintenance of a structure based on a code? Right now, there's not many ways to deal with that, but we need to deal with that too. Lack of standardization of service life goes back to the standards not having service life requirements. And then obviously sustainability and resiliency is part of a lot of the discussion that we're seeing a lot for carbon reduction. But then when you go through the analysis and calculations, they're not recognizing durability and service life of concrete to make those calculations. So all of a sudden you end up with a lot of good things that we can talk on a table, but truly, are they truly understanding how concrete structures can actually perform better than many of the other materials, right? And that's a gap in the industry, big gap in the industry right now with the sustainability efforts. So then when we talk about durability, we're going to get into basics now, right? The ability of concrete to resist a weathering action, chemical attack, abrasion, during inspected service life. That's a Portland Cement Association description. And then there's recognition to also do the damage and deterioration that it's related to durability, right? It's a presence of harmful elements. So it needs to get into the degradation of a structure, right? It degrades the ability of the concrete to resist a certain type of weathering condition, okay? So there's obviously impacts into the structure when we talk about durability, right? There's going to be exposure conditions that affect that, internal effects of the material chemistry, the quality of the materials we use to produce it are going to impact all that, right? And for a certain durability, requirement, you can have a certain service life, but it doesn't mean that if you have a durable concrete, right, all of them are going to have the same service life, right? So that's important to understand. Because then service life, can be defined in many different ways. And that's where it gets interesting. Even when you look at the definition in the different standards, it can tell you it can be repairs, it can be the in-service condition of a structure, it can be the actual uses, so it becomes more of a serviceability of the structure, right? But it's not necessarily on the technical side from a durability perspective. Sometimes it is more about the use, about the safety, about the amount of effort you need to maintain the structure in service. So all of a sudden, service life have a lot of definitions. But in simple terms for today, it can be defined as a time before a major maintenance is required, right? Let's keep it simple, just so we understand that. So now if we think about that, you can go and meet all the durability requirements in a code, and it doesn't mean that you're going to meet a service life. And actually, if you want to go through the exercise, just go through any code and run the calculations and to determine what is the service life requirements that I have for that structure under a certain condition. And you can change the different exposure conditions and you can see the service life is going to change. However, the concrete is durable per the code, right? But it's likely not allowing the concrete to be serviceable for the amount of years that you want to meet, right? So you need to understand that. And then when we talk about maintenance, we talk about different type of maintenance, right? It is normally expected as when you have a house or you have a car that you need to provide maintenance, right? Now, at what level is normal, at what level is major, right? There's a point that you say, I need to change my car because I'm spending too much money, right? It's time for me to change the car, right? So the same happens with concrete. There's a point that you say, I need to make all the changes of oils, I need to change the tires, I need to keep it, in good alignment with the performance I need, but hey, do I need to change it? Most likely not. There's a point that you're going to have to change it, right? So think about it that way. And then it's important to understand concrete as a material is long-lasting, durable, and a very sustainable material. There's no other material in the world right now that exists that has the amount of volume, right? That has the versatility of getting everywhere in the world and building houses, bridges, highways that can stand over 100 years. Doesn't matter how many research you do that you can show that in a little cup in your lab, it shows better sustainability from a little volume perspective, trying to scale it to the level of concrete. There's no concrete in the world. There's no material in the world that can be better than concrete for that purpose. Now, can we get better? 100%. Yes, we can get better. But it's important to understand there's no material right now better than concrete to build infrastructure. So then the principles of durability. What do we need to do? There's three main things I'm going to mention. Ensure the concrete properties are met. What does that mean? We need to start first by specifying the concrete correctly. We need to make sure that one of the things that I always say, not many people understand, that for you to make concrete durable, you need to make sure concrete is workable. Think about that fundamental basic. It's not very complex. For you to make sure concrete is durable, it better be workable. You know why? Because if you cannot place it, vibrate it, consolidate it, and finish it, that concrete is never going to be durable, right? So the fundamentals of concrete properties need to be met, right? You need to make sure that the concrete is strong, concrete is workable, concrete is durable, and somebody needs to pay for it. So you cannot make it be $5,000 a cubic yard because you know what's going to happen. Nobody's going to use it, right? So you need to understand all of these balance together to come up with concrete. Obviously need to make sure the properties are met. Then about the degradation mechanisms, make sure the concrete is durable to all the degradation mechanisms you have. You're going to end up with corrosion exposure conditions, freezing and thawing, sulfate attack, right? You may end up with internal mechanisms like dilated ring formation and ASR, right? All of those, you need to make sure you manage them, right? Deemed to satisfy what are the needs for that concrete to be durable. And there's always going to be other things that are going to be impacting the concrete exposure conditions and durability, which is going to be shrinkage, scaling, cracking. Cracking is a big deal. It's not that easy to manage it at a code level, at a standards level, at a design level, construction level. Cracking is always a problem, right? But how do we manage it? How do we actually come up with a consensus-based solution that we can say, you know what, we know that it's not going to be crack-free, but what is the level of cracking we can tolerate? What are the repairs we can manage? And how we can all work together towards the right solution. It's a very important that cracking, when we talk about cracking, is a client, designer, concrete contractor, concrete producer issue. It's not a concrete producer issue. It's not a contractor issue. It's not a design issue. It's everybody, right? Everybody needs to be in that game. Then we talk about corrosion strategies. How do we mitigate corrosion? How do we control corrosion from occurring in the rebar? Many solutions, right? But which one is the solution that works for you? Is it just making sure you make a better mix, and with the better mix, all of a sudden you improve the corrosion resistance? Or do you need to actually go and change the rebar? Or do you need to actually think about a surface treatment that is going to protect the concrete from being damaged, right? Or it's a combination, a little bit of everything, right? You need to make that strategy decision to improve corrosion resistance. And then service life. When we get into service life now, we get into a tool. It's a tool that helps you understand the performance of that concrete under a certain condition. Now, I always say, you can use the same level of exposure conditions with the same concrete, the same design, and there's always one part that is kind of managed by that design engineer. the reliability, the risk analysis, right? A 50% reliability design is not the same as a 95% reliability design. And all of that is part of the input on a service life design, right? So you need to understand also what is your level of risk that you can tolerate, right? And that needs to be established at the design level, at a client level, because a cost of a structure is not going to be the same at a 95% reliability and a 50% reliability. You can think a municipal bridge, likely a local bridge, can be managed at a 50% reliability. Small, you have alternative ways of going around, a small expenditure, right? If you maintain it, you can do it. But if you go to a monumental bridge that is crossing, two main cities, right, and you don't have a way around, you're likely getting to then in a high reliability with higher costs, and then you need to put different levels of effort, right? So all of that is even impacting how we look at service line. So, but the model, right? The model is pretty much assessing initiation of the material. Propagation gets into what level of damage you can tolerate, right? So you initiate pretty much tells you how long is the time that it takes me from point A to point B to get there, right? If I have a contaminant that we need to understand the life that it takes to get from point A to point B, how long does it take me to get there? Now the propagation is once that gets there, how long does it take me to actually create a damage, right? To actually propagate a level of damage that then I need to maintain, right? Or I need to control. And then obviously the service life becomes more of a user-defined consideration. You may actually, as a user, define the initiation period as the most critical point for you. But then that costs money. That also is completely different solution than saying, hey, I'm going to live with my initiation propagation because I'm going to actually tolerate some level of damage in the life of that structure that I'm going to maintain, right? And all of that creates a different level of expectation. A definition for initiation, more conservative, doesn't allow propagation, right? A definition of initiation and propagation, also technically correct, but then you have a different way of managing that level of damage, right? So you need to incorporate maintenance. Then understanding the different, components of the structure and exposure conditions. The bridge deck, the substructures, the foundations, all of them are going to have different conditions. Some of them are going to be submerged, some of them are going to be partially submerged, some of them are going to be exposed to the isochemicals chemicals directly, some of them are going to be splashed, some of them are going to be airborne. All of them are going to be different conditions you need to consider. However, all of them in that case are exposed to chlorides, if you think about it, but the level of chlorides is going to be different. The type of process to get from point A to point B is going to be different because the medium is different too. So all of those things are important. And then once you understand all that and you have a model and requirements, what is the level of effort that you're going to spend looking at the service life, right? In this case, I'm showing the concept of the FIB, which is a probabilistic analysis, Monte Carlo type of simulation, running a lot of variations, right? Similar to a lot of the things that have been discussed today, but in a completely different analysis, which is more probability and an analysis of statistics, right? Where you get into what is my level of risk and reliability. In this case, I put a curve for a 90% reliability, which means that you have a 10% of failure allowed, right? Where you say, hey, in my whole analysis, I'm gonna allow this little allowance of failure, but hey, if I do that analysis for that level of reliability, this is what I get, right? So that's the concept of the FIB, just to keep it simple. And then understanding the tools. This is a tool. It's not going to give you the entire spectrum of everything you can think about. It's just a tool. So what the tool is telling you, right? The corrosion-based analysis to determine time to require to initiate and propagate damage, right? Qualification of the concrete with testing, rebar protection and mitigation, right? You can make determination of that. You can make a determination of the strategies of maintenance too. And that's what we know, what we don't know. The development of concrete is based on analytical modeling using current knowledge, right? So what we know today, we're using to determine what's going to happen in 100 years, right? We don't know what's going to happen in 100 years, right? It's a tool, okay? The statistical predictions are based on probable conditions reliability assessments. So again, we go back, it's tools with the analytical knowledge we have today. Does not account for degradations of other conditions. So when you look at service life, it's a corrosion service life. It doesn't tell you what's going to happen to the freezing and thawing damage, cycling that is happening, or a sulfate attack condition, or if you have ASR, what's going to happen in 100 years. None of that is done in a service life analysis. Or you're looking at corrosion-based issues, okay? And again, I reinforce, it is a tool, okay? So you cannot guarantee the future. We're trying to assess the level of effort that you can put to understand how I can mitigate issues in the future, but doesn't have a level of guarantee that you can say nothing is going to happen, right? Nobody can say that tomorrow we're going to get something that we don't expect, right? It's a predictive tool, okay? So it's important to understand that. So then with that, the last portion of my presentation showing you some examples of where we're using that and where we're seeing that. So you can see that this is not just voodoo science. This is not just somebody in a lab running numbers. This is actually something we're doing today, and it continues to happen today. And obviously in Hawaii, we have big projects that actually will go through that and are going through that. So this is an example of a light rail structure. This one light rail structure was in Canada. We look at 100 years. We look at different conditions, high strength, high early strength. No specific rebar type was specified. In this case, we want 100-year life, but there's no service life defined in the specs. So it's 100 years of what, right? I'm going to ask the three of you, give me 100 years. You're going to figure out what is 100 years to you. You can think it's initiation. You can say it's initiation and propagation. You can think of, well, Oscar, I believe it's something else. That's a problem, right? That's a problem. These are true projects. It's a problem because the specifications are not defining. The clients do not understand it. The design engineers do not understand it. So we need to find better ways of doing that. Prescriptive mixed design requirements, which is another issue, because now they're telling us what they want in the materials, but they're not understanding that they also want 100 years. It's like me telling you the way you're dressed today, you're going to run the Iron Man, right? And you're going to run it today you're going to do it with dress shoes and with a jacket and with a backpack. And I'm going to tell you that you need to do all that, dress like that, but you need to meet the requirements I'm going to put you in a certain amount of time. You're going to be, Oscar, that's impossible. I can do that with my shorts and with nice tennis shoes, but I'm not going to do it like this with a backpack on my back, right? When you put prescriptive requirements, that's what you're telling the builder to do. You're not giving the opportunity to be successful. Then obviously conflicting requirements of performance, exposure condition and mitigation strategies couldn't be used correctly because they also limit the amount of mitigation that you could use, but then you have issues with the ASR, for example. So how are you going to mitigate if you're not allowed to use a certain amount of mitigation? So you have conflicting requirements there. Immersed tube tunnels, this is actually in the United States, precast segments, immersed tubes, and pretty cool project because you would actually build all that in a dry dock and then float into the ocean and then sink them and then, level them in the ocean and create a tunnel. So pretty cool, right? 120 years, 120 years. Service life, again, just the time defined, but no description of what it means, right? So now you need to figure out what it is. The high performance concrete plus surface treatment could be used. So in this case, they were allowing the surface treatment to be accounted for the time of service life. And then black rebar is deemed acceptable. Now, when you allow black rebar, you don't have a rebar that is corrosion resistant. So all of a sudden you need to manage better your cracking, right? Because once you allow cracks, then you're going to have completely different issues to manage, right? So it was a little bit of challenging. What that means is that then your mix becomes more difficult. Because if you need to create mixes that are more cracking resistant, all of a sudden they're not that workable, right? And you have all this rebar that the design engineers want. So all of a sudden you have more issues now. How do you make the concrete workable to make sure that all of a sudden you can consolidate it? But then because the mix needs to be, more difficult because we could not use a corrosion resistant rebar, all of a sudden it becomes a challenge for construction, right? So how do you manage that? Okay, so there were a lot of different issues with that, and obviously with mass concrete because there were larger portions, so we need to put cooling pipes. So all of that, obviously, we were able to manage all that. But we spent almost over a year, defining the right mitigation strategies, trying things, doing trial after trial to get the right solutions. So it takes more time, right? And then this is the last one, and this one is also in the United States. Was pretty cool because it was a full rise of a bridge while it was actively open. So we had to switch traffic and all that, all precast. So it's a full precast bridge. Piers were precast. So substructure, superstructure is all precast, segmental, post tension. Pretty interesting job, right? And in that case, we had the opportunity of using stainless steel and epoxy coated rebar. Another issue was then the problem with surface line not being defined, then trying to manage the cracking tolerances was not appropriate. A lot of the conditions that were analyzed by the designer were already recognizing cracking was going to be an issue in some locations. and then obviously trying to work with the client on accepting level of cracking, fixes of the crack. Clients asking for, I want 100-year repair. Well, 100-year repair doesn't exist. There's no material that is going to be guaranteed for that, right? And there's no material that is going to be maintenance free, right? So all of a sudden you need to manage all the challenges of how much it takes to get that done. So I'm going to get you to dinner. So you have 2 more minutes to make it on time. So on the closing remarks, the point to be made is that the concrete is a versatile material, right? It's very durable and it can achieve a lot of good things for long-term performance. It makes concrete sustainable and it improves the life of the structures, right? Properly specifying the concrete is extremely important for concrete to be better quality, more efficient designs, improve durability, and also be more sustainable too. The use of concrete durability in design with service-like tools actually improves the way that you implement durability solutions too. So extremely important that we understand there's durability, there's also service life tools that you can use to improve the performance of the concrete, right? And then as we see a lot of the global initiatives going on and local initiatives for sustainability to reduce carbon footprint, we as an industry need to make sure that those solutions also account for recognizing concrete is durable, concrete service life needs to be part of that solution. Right now, they're not accounting for that, and it's extremely becoming a problem. So with that, I believe I made it on time, 1 minute early. So thank you so much.
Thank you so much, Oscar, and great to see a contractor on schedule.
Yeah, you saw that.
So we'll take maybe 1 or 2 questions.
That's funny.
In the real life, shouldn't we see that from practice to standard more, or from standards to practice?
Yeah, so we are trying to bring more of the practice to the standards. You're correct. That's why you're hearing people like me talking in an event like this. So we're trying to actually bring more. It's not that easy to bring the practitioners into the standards. And we want more designers, we want more clients, we want more contractors in the standards. Academics are always going to be there and they're very welcome, but we need also more of the field practitioner experience. So we can actually put requirements that are realistic and can be implemented so you can have the right solutions to actually build the work. Many times, if you know how the standards work, sometimes people are just fine-tuning equations and go back and forth over 10, 15 years fine-tuning an equation that doesn't create any value to the client. It's just an equation that actually now maybe has a little more precision, but that precision doesn't create value to the actual final solution, you know? So I hope what I'm saying is that, yeah, more field practitioners come to the standards and we can have better standards. Yes, I agree.
Any other questions?
So, great presentation. Thank you, Oscar. In the real situation, oftentimes you may, just like you said, corrosion may not be the only stressor. So if you have police, you know, the couple effects, do you think there's a need for better models to take care of 2 or 3 different stress? So maybe one-on-one limit state when it comes to suicide.
Yeah, and the European, you know, FIB group is working on a few other models that have not made it all the way to North America for sulfate attack, for example. There's some people that talk about freezing and thawing simulations that they can also do and try to create models to represent that. There's no consensus on that. We know that there's more consensus on the corrosion side of it. So that's the one we can implement in the industry. The other ones become more of, there's knowledge out there at academic level that they can get some solutions, but there's no consensus. So I foresee the future, yes.
One example I'm thinking is like, you know, in Washington State, we have a lot of seismic activities. And the seismic activity definitely will create some cracking and affect the ability of the concrete in resisting chloride ingress. And vice versa, when you have corrosion, you have less ability to resist seismic activity. So, you know, it's kind of like a joint action of the two.
Yeah, they just because you said it, the structural behavior and the material properties, when you look at the design and the codes, are not necessarily tied together. You look at how you satisfy structural behavior, check. How do you satisfy the material properties? Check. What you mentioned is not yet there with the codes. So you can allow actually cracking occurring from a structural behavior. Doesn't mean that the durability performance of the material is compounding the effect of that cracking that the structure is tolerating. It's a big issue because all of a sudden, you know who deals with that problem? It's not the designer. It's actually the contractor that has to deal with fixing all the cracks that the design allowed, right? But because there's no recognition of how to mitigate those cracks, then all of a sudden the producer, the contractor, the client is going to be dealing with it. So yeah, there's a lot of more to deal with that in the future. I don't think there's a solution right now for it. Yeah.
Enjoyed the presentation.
Thanks.
What are the implications?
Is there like sort of a larger?
Yeah, and what you're asking for all of you that didn't hear is more about the global changes impact to the organization that I belong. And if it's more of a local project to project or more of a global company-wide issue. We right now have an initiative that is working on understanding better the effects of that. So I can tell you, we do care. We are moving to understand what exactly that means to us. We're in the forefront of obviously understanding how we can provide solutions to the clients, how we can provide, tools to the construction teams, how we can improve the way we design. So we are moving and connecting and trying to understand what we got as a company and also at a project level, a district level, market level, because the solution in Hawaii is not the same that we have in Seattle, right? In Hawaii, we have a unique issue, which is an island effect. And I was born in an island, just in the other side, right? I'm come from Puerto Rico, so I know exactly what it is living in an island and being part of the United States. But here we have an issue. You only have one supply of materials coming through one pipeline, right? You get one type of fly ash, one type of cement. So when you think about solutions from a concrete perspective, there's a challenge and a limitation, because you cannot all of a sudden say, I'm going to have 5 types of cements, 5 types of fly ash, because you don't have the facility to do it or the market to do it. So yeah, the solutions in Hawaii will be different than Seattle or Canada or in the middle of nowhere in the Northern Canadian territories. But yeah, we are trying both. We're learning a lot, as the same way we are all learning as industry professionals. The changes in carbon reduction, sustainability, and resiliency is making us better professionals, and we're learning. I don't think anybody's yet there to become the expert, because every day we learn something new. So we are also learning as a company. Yes.
One last
One.
Okay. When you are doing planning for durability and you know certain things might be of concern, are you also providing any recommendations related to what should be monitored and how it should?
Yes. What you're talking about is more about the implementation of monitoring systems and if you have any specific quality control during construction, right? So
Yeah.
you have both. Yes, you have both. So there's projects that you don't have to do any of that, right? Remember, the requirements are going to define the level of effort you put, right? So depending on the level of effort, you're going to have projects that you only do the design analysis, put the requirements, build the work to those requirements, right? Those sometimes are more deterministic, simplistic projects. Where you get in the in-between, they're not that probabilistic. You may actually have more of a quality control program to make sure that things are built to that requirement. And in some other cases, you get into full probabilistic where you're actually monitoring, the structure in the life of that structure. So then the owner and the people that are going to be operating it can actually use that information to maintain it too. So yes, there's all different levels. It depends what level is specified and is obviously contracted for. Yes.
Okay, well, thank you again so much, Oscar. Great presentation, and we'll continue to be better.